Let's look at the last page of section 2.2 notes. We're looking at inferring properties of a polynomial function from its graph. So we're given the graph. We're trying to tell some important parts or important properties of this. The first part is asking us to identify the increasing interval. So where is this going up from left to right? This graph is going up from that number to that. I can't really read these numbers, but I'm just going to go ahead and highlight these first, okay? So this graph is increasing in those two orange highlighted intervals, and we need to use the x-coordinate, not the y-coordinate, to tell these intervals. And this looks like a 3, and this value is 5. So the first increasing interval is from 3 to 5. And this starts going up again at 7. And assuming this graph continues this pattern to the right, we can go ahead and say positive infinity for the right end. Okay? All right, so that's the increasing interval that's going up from left to right. Going up from left to right. Let's look at decreasing interval. Okay, so where is it going down from left to right? So it's going down from left to this point, and it's also going down in between 5 and 7. So let me write down these decreasing intervals. First one, it started somewhere from the negative infinity, right, to the left. And what I mean by negative infinity is to the left side of this x-axis, to the left side of x-axis. Because I know what someone will accidentally think. I'm not saying pointing up is negative infinity. Going up is positive infinity. But when I use negative infinity, I'm saying to the left. Okay, so from negative infinity to this point 3, and the second decreasing interval is from 5 to 7. So I hope you can see this. So the decreasing intervals that I colored in green, these two intervals, the function was going down from left to right. Okay, how about local maxima? How about local maxima? Let's go ahead and find the local maxima. I see one right here. I see one right here. Okay, so the local maxima is at 5, -1. I'm not sure if they're going to ask you for an order pair format, but basically I'm saying x is equal to 5 and y is equal to -1. So if they ask you for the local maximum value, it's going to be -1, okay? But if it's asking for where is the local maximum, you have to tell them it's x is at x equals 5. All right, let's find the local minimum then. The lowest points of the valleys, one right here and another one right there. I have two local minimum. So one of them is 3. And how low does it go? It doesn't really say it. Oh, I think I know. I think they're going to just ask you to identify the x value. So I'll go ahead and say it's at x equals 3 and it's at x equals 7. Because I was trying to read that y value, but you see how it is not exactly at -6, so it's like -5 point something. So I am thinking your Alex homework will just ask you for the location of these local maxima and local minima. So just give them the x coordinates. So I'll change the local maxima to just x equals 5. Okay, what can we say about the sign of the leading coefficient of f? Well, looking at how both ends are rising up, rises to the right, and rises to the left, we know this is even positive, right? So this is going to be an even degree because both ends are doing the same thing. Okay, if ends are doing opposite things, it's going to be odd. But we know this is going to be an even degree function Because both ends are going up, up. And because the sign, because they're both going up, up, we know the sign of the leading coefficient is positive. And this is because end behavior rises to the left and right. So whenever the end behavior is the same to the right and left, we know the function must be an even degree, okay? But we know this is a positive leading coefficient because both ends are pointing up. If they were pointing down, then we will say it's going to be negative. I think Alex asked you to do one more step, okay? And that idea connects it with something called the turning points. We'll do more with this, but I'm going to go ahead and ask you to identify how many points this graph is turning. So I'll go ahead and say turning points. Okay, so we're going to follow the graph and see how many times this graph is turning. So it's going down, but then, it was going down. But at this point, you see how it turned? One turning point. And at that point, another, it changes the direction and goes down. And then it goes back up. So how many turning points do we have? We have 3 turning points, okay? So say that we have 3 turning points. Hold on, let me move it. We have 3 turning points. So that means degree has to be greater than 3. Okay, so I remember seeing this problem on your Alex homework. They ask you for possible degrees. They list things like this, degree. And then they give you 1, 2, 3, 4, whole bunch of them, 6, 7, 8, I don't know how far it will go. But say that you get something like this. We know because of the end behavior, the degree is even. So you're going to cross out all the odd ones. This must be an even degree, so you cross out all the odd ones. So we have all the even numbers left here, but because it had 3 turning points, what we know is that the degree has to be greater than 3. Degree always has to be greater than the number of turning points, okay? So we're going to cross out 2 because 2 is smaller than 3. So the possible degrees, the only answers that I need you to click on when you're doing this homework is 4, 6, or 8. To me, it looks like a 4th degree function, but who knows, maybe they added some different terms to make a 6th degree or 8th degree looking like a W-shaped function. To me, it looks like a 4th degree function. But this is how you would do this. Remember, degree has to be bigger than the number of turning points that you have in the graph. Let's do one more example. It's called you try. So how about you can stop the video, you try this, and then you can, fast forward a little bit to watch the correct answer. But I'm going to go ahead and just do this as one more example, okay? So first of all, increasing interval. It's going up in that interval. It's also going up in that interval. I don't even get mad at my iPad anymore. It probably did too much work today. Look at that. Guys, we did so much work. Okay, so let me go back and try increasing interval again. It's increasing, it's increasing. So those 2 intervals, if I write this down, it's going to be from -8 to -6. I'm reading the x coordinates of these special points, -8 to -6. And -4 to -2. -4 to -2. So these are the increasing intervals. That's the only the ones I see. All right, now let's do the decreasing interval. It's going down all the way from the left to this point. There's a decreasing interval in the middle, and there's a one that's going to the right. So if I write 3 decreasing intervals, they are going to be -∞ to -8, comma, -6 to -4, comma, and the last one is -2 to positive infinity. I can't remember if you guys had to use a union symbol, but if they ask you to do the union of sets, just put the u's in between, okay? All right, now let's do the local maxima. Local maxima, where are you? Let's find them. It's not only this point, but also this point. Okay, so we have two local maxima, and those happen at x equals -6 and x equals -2. All right, how about local minima? We have a local minima down here and another one right here. So local minima happens at x equals -8 and x equals -4. Now, what about the even or odd degree? This graph is pointing down to the right. So it's a decreasing function. Because this is going down to the right, this must be a negative leading coefficient function. Because it's going down to the right. Anytime it is going down to the right, the leading coefficient will be negative. Okay, that's a good rule to kind of write down. Anytime that the right end behavior is going down or falling, then the sign of the leading coefficient is going to be negative. Okay, all right, how about the right end though? It's going up to the right. Now you notice something. The end behavior are opposite. One end is going down, the other end is going up. So because they have opposite end behaviors, this must be an odd degree. Okay? Now, this is how much I will ask you, but Alex will ask you to identify possible degrees. Okay? And they will list numbers. 1, 2, 3, 4, 5, 6, 7, 8, da 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 da. I don't know how many they do. But in order for you to answer that question, we're going to have to look at how many turning points. Okay? We see 1, 2, 3, 4 turning points. 4 turning points. And turning points is just nothing more than whenever the graph switches the direction. It was going down, but then poof, it went up, and then it goes back down. So anytime you have local maxima or local minima, those are your turning points. Because we have 4 turning points, degree must be greater than 4. So remember that. Let's go ahead and cross out some of the wrong answers. So first, we know it must be an odd degree function. So cross out all the even ones. Can't be 2, can't be 4, can't be 6, can't be 8. So it can be 1, 3, 5, or 7. But because we have 4 turning points, we're going to cross out anything that is smaller than 4. 3 can't be it. 1 can't be it. Therefore, the only 2 possible that I listed here is the degree of 5 or 7. So when you get to this, and the only reason, guys, I added this problem to this note is because so many students in my previous classes emailed me about it. So if you guys find another topic that you want me to go over, just write me an email with that topic name. I will make sure to create some resources for you. So I hope this was helpful. We are done with section 2.2. I want you to come back and work on section 2.3, the online lesson later. Have a great day.